So hello everyone. It's the first session of the afternoon, and it will be on algebraic attacks, and there will be three presentations. And the first presentation is improved attacks on low MC with algebraic techniques, and it's a paper by Yimeng Sun, Jiamin Sui, and Meiqing Wang, and Yimeng Sun will give the talk.
Okay, thanks for the introduction. I will start my presentation. I think low MC is a very famous S-plane block cipher family. It was proposed at European Cryptology Conference in 2015. The selection of parameters of low MC is very flexible. For example, it uses partial or complete S-box layers, and its affine layer selection is also random. The figure 1 shows the round function of low MC. Low MC has been utilized as the underlying block cipher of the digital signature algorithm PICNIC. So, the security of PICNIC is directly related to the difficulty of recovering the secret key from a single plaintext or ciphertext pair. Because of the importance of low MC, there have been a lot of attacks against it. We focus on the last two types of work. When there are one or two plaintext or ciphertext pairs, we improve the two works marked right. Next, we will introduce two methods that we need to use to solve polynomials. Now, consider a system of unblown equations in U variables denoted by E, like equation 1, and the algebraic degree of each EI is bounded by D. We divide X into two parts, Y and Z. So, how do we solve this equation system? Let's start with the first method called the crossbred algorithm. We find that each EI can be written as equation 2, where each element in M and B is linear and quadratic in Y. After Gaussian elimination to equation 2 to get equation 3. Equation 3 is a linear equation for Z. Then we search for all possible values of Y and solve for Z according to equation 3. In this way, we successfully solve the equation system. The second method is Dinner's algorithm. The core ideas of this algorithm are as follows. We randomly take U1 plus 1 different equations from E and construct the new equation system E tilde. We find that a solution of E must be a solution of E tilde, but the inverse doesn't hold. We choose to enumerate the solutions of E tilde and then verify them by E. Let's build a polynomial A tilde. We find that A tilde X equal to 1 if and only if X hat is a solution of E tilde. So we only need to enumerate all possible X such A tilde X equal to 1. The difference enumeration attack consists of two phases. One is the difference enumeration phase, and the other is the key recovery phase. In the difference enumeration phase, we enumerate all the possible differential trios to recover the compact differential trios. In the key recovery phase, we retrieve the full key from the recovered differential trios. Now, let's take a look at the difference enumeration phase. First, choose an input difference delta 0 such that there will be no active S-boxes in the first R0 rounds. Second, encrypt a plaintext pair whose difference is delta 0 for R rounds, and obtain the corresponding difference delta R of the ciphertexts. Third, enumerate state differences backwards from delta R for R2 rounds, and obtain the state difference delta R0 plus R1. The next thing we focus on is what to do with the R1 rounds in the middle. Let's take a look at the figure 3 and figure 4. The previous work introduces variables to all S-boxes in the middle R1 minus 1 rounds to represent their output differences and obtain a linear equation system. We denote this equation system as equation 4. After Gaussian elimination, we get equation 5. Then we build the table du in the offline phase. At the online phase, we enumerate all the free variables in equation 4. But there are still problems of this method. When the number of detected rounds increases, the time complexity to enumerate all the free variables grows, since we still assume them all independent variables. It is possible to improve further. Now, we propose a new method to deal with the difference enumeration phase. The figure 5 shows the new difference enumeration attack framework. Our method is divided into 2 phases. The first phase is the enumeration, and the second phase is the construction of higher order equations. Similarly, we also introduce variables to all S-boxes in the middle R1 minus 1 rounds to represent their output differences and obtain a linear equation system. In the offline phase, we focus on the last omega prime rows in the matrix M2 prime instead of the omega rows. Then we build the table du prime. This is just different from the way it was before. We introduce nonlinear equations of degree 3 for the unknown variables in the online phase instead of enumerating them, and then solve the equation system utilizing Dinner's algorithm. In the key recovery phase, we retrieve the full key from the compact differential trios. Starting from a ciphertext, checks the S-boxes in the backward direction round by round and one by one. For each inactive S-box, we introduce intermediate variables to represent its input. If we denote the number of active S-boxes and the number of inactive S-boxes by A and B respectively, we can obtain 2A linear equations and 14B quadratic equations in terms of K plus 3B variables. The previous work uses Gaussian elimination and the linearization technique. However, this creates a strong constraint on the value of A due to the number of independent variables introduced in the linearization technique. This results in lower success probability. In our attack, we construct 14 lambda quadratic equations for the first lambda inactive S-boxes, and not for the B inactive S-boxes. We use Gaussian elimination and the crossbred algorithm to solve the equation system. The success probability of attack is about 0.9. The table shows that the security margin of some instances can be reduced to 3 or 4 rounds, and we improve the success probability from around 0.5 to over 0.9. Like this and this. Now, we focus on low-MC instances with full S-box layers using only a single plaintext or ciphertext pairs. From figure 6, we can see that for an S-box, if we get 2 input bits, the S-box can be linearized for free. Moreover, the input to the S-box belongs to the space denoted by B. Let's give a small example. Consider the case when 2 input bits are both equal to 0. Then we can have the space be 0, 0, like this. The figure 7 shows the attack setup for even and odd rounds for low-MC instances. If we get 2 input bits for each S-box in the first round and linearize the first round, we can then we use the meet-in-the-middle method to get n equations at there and there. Because of the different guesses in the first round, we can divide the input into different spaces. For each guess given, we can get the associated function of the equations. We divide variables into two parts and randomly select L equations from the N equations. We find that a solution of EG must be a solution of E tilde G, but the inverse doesn't hold. We choose to enumerate solutions of E tilde G and then verify them by EG. Now, according to the proposition, we can solve for the variables. The red part of this table is our result. It's clear that the memory complexity is drastically reduced at the expense of a small amount of time complexity. Now, let's give a summary. For different enumeration attacks, we push the security margin of different instances of LOMC with partial nonlinear layers to 3 or 4 rounds. For the picnic setting, we drastically reduce the memory complexity for 5 or 6 round LOMC instances with full nonlinear layers. The security evaluation of different instances of LOMC under extremely low data complexity has not yet come to an end. Thanks for your attention.
A lot for the nice talk. Is there any question in the audience? No.
Okay, thanks. I got one problem on page 14. Why would you?
Sorry, wait a moment.
Okay. Why would you like to change the linear equation to high order linear equation to high order equation? Thanks.
When the number of variables is larger than the number of equations, if we use linear equations, the number of variables to enumerate is too large. So we use the higher order equations.
Oh, okay, thanks.
Thank you.
Is there any other questions?
Yeah, thanks for your presentation. I think you follow many of my works. So, and for example, in this figure, you said improve the offline phase by involving Dinius polynomial. I mean his algorithm. So I want to know the size of the nonlinear equation system that you use the Dinius algorithm to solve. Is it small or very? Is this very small or large? I don't know. I mean, the size of the nonlinear equation system, the number of nonlinear equations. I mean, is the number very small or slightly large? Yeah.
For each icebergs in the backwards direction, we introduce two nonlinear equations and solve them by utilizing Diner's algorithm.
I mean, if the number of
so sorry.
Oh, sorry. I mean, indeed for Diner's algorithm, I think if the size of the equations is not too large, maybe it has any advantage. I don't know. So will this be an issue in this attack?
The equation system is small.
Yeah, if it's small, maybe I mean, there's no advantage, I guess, I don't know. So I want to know whether this will be the case in your attack. So I want to know whether the number of nonlinear equations is small or large.
Do you mean you want to know the number of nonlinear
Yeah.
equations?
Yeah.
This I forget it.
Okay, it's okay.
Oh, sorry.
Okay.
We still have for other questions. If not, maybe I have one. Do you think you use all possible equations and you can construct with the only one plain text ciphertext in this setting? Or if you need new equations, is it needed to have a second pair plain text ciphertext? Or in the equation system you build, do you build all possible equations in this setting compared to the problem?
Sorry, I don't understand.
The equation you build.
This page.
No, not this page in general. Do you in the paper you presented? Do you think the system of equations you have captures all possible equations that you can build from the plain text ciphertext pair? Or
Yes, one pair. Or
one pair.
One pair.
And the equation you have captures all the information, all the possible information you have. That's my questions. Or is there some missing information somewhere?
The equation system is n equations, starting from a plain text and starting from a ciphertext in the forward direction and the backward direction, means in the middle, and obtain the n equations.
Okay, thanks.
Thank you.
So let's thank the speaker again. So the next talk of the session is Algebraic attacks on rain and aim using equivalent representations. It's a paper written by Foucan Liu, Meyron Marzoun, Morten Oygarden, and Willy Meyer. And Meyron Marzoun will give the talk.
So the first step in launching algebraic attacks against cryptographic primitives is to model it as a polynomial system. However, there exist many ways to model a primitive as a polynomial system, and not all of the modelings have the same solving complexity. So in this talk, I'm going to present some efficient and equivalent representation of two primitives, rain and aim, so that solving them has less complexity than the desired security level. So aim and rain are two primitives that use in post-quantum secure digital signature schemes, Aymer and Rainier. And Aymer and Rainier are digital signature schemes that are based on MPC in the head design paradigm. And Aymer is currently a round one candidate for the NIST post-quantum competition and one of the 4 digital signatures that advanced to the second round of Korean post-quantum competition. And Rainier is a very efficient signature based on minimalist symmetric key cryptography. And important thing about the designs that are based on MPC in the head is that their security mainly relies on the security of the hard problem that is the building block of those signatures. So in case of the Aymer, the security relies on the security of the one-way function aim. And in case of Rainier, it relies on the security of the block cipher rain. And I'm going to talk about the algebraic analysis of aim and rain in the next rest of my talk. So the goal of algebraic attack is to uncover confidential data by modeling the primitive as a polynomial system and try to solve it efficiently. So imagine that we have a cryptographic primitive and we can model it as a polynomial system with n variables in n equations. Then solving this system entails finding a variety V of set of all the points in our space that all the polynomials in the system are vanishing over all the points. And in our work, we use three primary techniques to solve polynomial system: fast exhaustive search, cross-paired algorithm, and polynomial method. So when we have a polynomial system, the most naive way to solve it is to iterate over all possible solutions and check if they are the solution to the system. So for the case of our interest, where we have like n variables over a binary field, the possible number of solutions is 2 to the n. And each polynomial of degree, each polynomial has n choose j monomials of degree j. So total complexity of iterating all possible solutions and evaluating the polynomial is 2 to the n times the number of monomials that we have in the system. However, there exists a more efficient way to solve to iterate over all possible solutions. And we can compute a polynomial for all possible points in the space with complexity 2 to the n times the degree of the polynomial. So when the degree is small, this is almost same as 2 to the n. And we can use the fast exhaustive search to solve a polynomial system with time complexity 4d times log of n times 2 to the n, where d is the algebraic degree of the system, and with memory complexity n squared times the number of the monomials in the system. Another approach to solve polynomial systems is cross-paired algorithm. The main component of the cross-paired algorithm is Macaulay matrix, which is also the main component of the many other polynomial solving techniques that are based on normal form methods. So a Macaulay matrix of degree d of a polynomial system is a matrix that the columns are indexed by the monomials up to degree d, and the rows are indexed by the polynomials of the system multiplied by monomials, as long as the degree does not exceed d. And the idea of cross-paired is to choose a parameter, k, and try to eliminate all the monomials in the system that has a degree larger than some d prime. And then when we guess the rest of the variables in the system, we would have a system in k variables with degree d prime that is hopefully easier to solve. And in some intriguing cases, guessing the sufficient number of variables would lead to a polynomial system that consists only of linear equations, and then it's trivial to solve. And the last approach that I'm going to talk about is polynomial method. And the idea of polynomial method is to find the solution to a smaller set of equations and then check if it's also the solution to the whole system. And the good thing about polynomial method is that it has accurate time complexity and memory complexity. And for case of our interest, a quadratic equations over binary field, the time complexity is n squared times 2 to the 0.815 n, and memory complexity is 2 to the 0.63 n. The issue with polynomial method is that when the system is overdefined, it doesn't gain anything. And in general, when the system is overdefined, it means that we have more equations, meaning that we have more informations about the solution. So we expect to solve it easier, but this is not the case for polynomial method. And now I'm going to talk about the security of aim and reign using the approaches that I described. So reign is a MPC-friendly block cipher, and each round consists of subkey injection, inverse SBox, and linearized polynomial. Linearized polynomial is a high-degree polynomial that, when we look at it at the bit level, it's just a linear function on the bits. So over f2 to the n it's of high degree, but it's a linear polynomial over f2. And in reign, the goal of an attacker would be to recover the secret key k from pair of inputs and outputs in constant data complexity. And we are interested in 2-round reign and 3-round reign, both of which were assumed to be secure in the original design. However, the designers suggest not to use 2-round reign because to have some security margin. and use at least 3 rounds for rain. So to talk about 2-round rain, let me first describe how it works. So it has 2 inverse S boxes, 1 linear S polynomial, and 3 subkey injections. And of course, the first step is to try to model it as a polynomial. And so therefore, we call the state after the first S box with V1, and then we can write, we can model rain 2 using a single polynomial. The issue of this polynomial is that it's of high degree, so we cannot do anything with it. Therefore, we transform it to a system of quadratic Boolean equations over binary field. So after converting it, we would have a system of n Boolean equations in n variables, and then it would be easy to solve. And yeah, we use polynomial method, and we showed that the time complexity of solving this polynomial for all 3 instances for like 3 different security levels is smaller than the security requirement. We are also interested to see if we can do better, have smaller memory complexity. And remember that I said that when we have a polynomial system and it's overdefined means that it should be easier to solve it because we have more information. So to have a more efficient attack, we try to define more polynomials to describe the solution. So one was the polynomial that was already describing rain. And we derive G by multiplying it with a linearized polynomial. And we derive another polynomial, H by multiplying F, which is the original polynomial, with a quadratic function of the variable V1. So both M and the quadratic equations are linear over F2, and both 2 and 3 would be quadratic still over F2, and they would be linearly independent from 1. So in general, we would have a quadratic polynomial system over F2 that has 3 n equations and n variables, so it's overdefined, and it would be hopefully easier to solve. And we will try to solve this polynomial system using cross-spread algorithm. But to analyze the complexity of cross-spread, we should be careful because the way that we generate those polynomials is like we are giving them structure. So at higher degrees, there would be cancellation, there would be linear dependency. So the Macaulay matrix at higher degrees would have probably less rows than we expect. So therefore, we have to compute the rank of the degree D Macaulay matrix for the degrees that we are interested to implement cross-spread, and we compute the degree for, we compute the rank for degree up to 4. And the next parameter that we have to compute is the number of monomials in the first I variables that have degree larger than 2. So if we have this number and we guess the rest of the variables in the system, then we have linear equation in the first I variables. So of course, first we need to compute this parameter that we want to eliminate all the monomials of the system that has degree larger than 2 in those variables. And then we want to guess the rest of the variables of the system, which are n minus k. And then we would have a linear system in the first covariables to solve. So naturally, we would like to minimize the number of variables that we want to guess and also maximize the size of the linear system that we want to solve, because solving linear system is very easy. Therefore, we define the parameter k, which is the maximum largest integer that if we guess the rest of the variables and eliminate the monomials that has degree larger than 2 in those variables, we would still have a system that is solvable. And in this table, you can see the summary of the different instances of cross-spread algorithm against instances of rain. And as you can see, the time complexity is very competitive with the polynomial method. And for the smaller security levels like 128 and 192, cross-spread is more efficient, while for the 256 bit of security, polynomial method is more efficient. And in terms of memory, cross-spread is much more efficient than the polynomial method. And a natural question would be if we can use the same approach to attack three-round RAIN. So if we try to model three-round RAIN using a single polynomial, we would have something complicated like the polynomial that you can see on the top. And the issue with this polynomial is that it has a term that is colored red that has a high algebraic degree. And since it has high algebraic degree, we cannot really use the polynomial, use the techniques that we know to solve it efficiently. However, we observe that if either of the inverse of the second linearized polynomial or the first linearized polynomial are sparse, then we can have successful attack. But this is not happening in the three-round RAIN because the designer made sure that the polynomials are indeed dense and sufficiently random. So the next design that I'm going to talk about is AIM. This is the one-way function that is used in AIMer signature scheme. It has a simple design. There is an input that goes through a parallel layer of Mersenne S boxes, then goes to a affine layer, which is randomized using some public initialization vector. Then there is another Mersenne S box. The output is then derived by adding the input to the output of the second Mersenne S box. And the goal of attacker here is to compute the input X, having access to the output and the public initialization vector in, again, constant data complexity. So there are 3 instances of AIM for the 3 security levels that NIST requires. And in all 3 instances, all except one of the exponent that is used in the Mersenne S boxes is a small. And we're going to exploit this small exponent and try to break the instances of AIM. So therefore, the first step is to model it as a polynomial system. We can just call the state after the affine layer with S. Then we can write input as a sum of the power of S plus the output. And also we can describe a state after each S box, again with the variable S and the output. And then just expand it, and we have some term that describe each S box using the output and the variable after the affine layer. And we are interested to calculate the accurate algebraic degree of the polynomial 6. Now, without loss of generality, let's assume that the last S box has the largest power. So we hope to find a way to get rid of it. And therefore, we write the equation for the last S box using 2 different approaches. First, we can just write it as a system of, we can write it as a polynomial of the S and the output, which is 8. And we also can write it as a polynomial of all the other S boxes, which is 7. And then the left-hand side of 7 and 8 are equal. So we would expect the right-hand side to be equal. And therefore, we can derive one polynomial that describes the solution of the AIM instance. But again, this is a very large degree polynomial, so we have to convert it to a polynomial system over the binary field. And after that, we would have a polynomial system that we can bound the algebraic degree accurately and then solve it using a fast exhaustive search because the algebraic degree is small. So here you can see the summary of the results for different instances of AIM. And in all the 3 cases, the complexity of the attack is smaller than the required security level. And yeah, so to conclude, the point is that the way that the polynomial system, a primitive is modeled as a polynomial system matters. We already saw earlier in Matthias' talk that generic coordinates like give interesting provable bounds, or in Katarina talk that reordering of the variables can affect the efficiency of the solving of the system. And here we saw that we can break 2-round RAIN, all instances of 2-round RAIN using polynomial method and crossbreed. We showed that if the linear layer of the 3-round RAIN is sparse, then it's not secure. And we use fast exhaustive search to break all instances of AIM. Thank you for your attention. And if you have questions, I'd be happy to answer.
Thanks a lot. Is there any questions? So I will have one on the sparsity of the matrices. So you said that if the matrices are sparse in some sense.
Yes. So if the matrices are sparse, we can write that term that has high algebraic degree by introducing sufficient variables with low algebraic degree, and then we can just solve it more efficient.
And I will have another question related to this. Do you think or do you believe it's the only criteria to say that it will, I mean, is it sufficient? Do you believe it's sufficient to have those two matrices not sparse such that it's not possible? Or do you believe there could be another criteria to write down this expression in a better way such that it could be interesting to look at it? I mean, do you think it's the only criteria to
The only
address the security?
criteria to show that if it's dense, then it's secure?
Yes.
Yeah, I don't think so. Yeah, but we have to see.
Okay. Is there another question? No? So maybe one last one. What you use here is that in the paper is that if you multiply x minus 1 by x, you have something that is linear. So that's why you build those quadratic equations.
Yes.
If you would have, do you think changing x minus 1 to another x to the power would drastically change the complexity of the solving?
Yeah, I haven't thought about that, but since this work, yeah, I didn't.
Okay,
think.
thank you.
Yeah.
Thank you, everyone. I can thank the speaker again. The next and the last talk of the session will be algebraic attack on FHE friendly cipher, HERA, using multiple collisions. And it's a work by Fukang Liu, Abul Kalam, Sanatu Sarkar, and Willy Meyer. And Fukang will give the talk.
Thanks for introduction. So we'll continue algebraic attack. And in this talk, I will give a very simple algebraic attack on FHE friendly cipher HERA using multiple cleans. And indeed, multiple cleans is slightly different from multi-cleans that was mentioned in the invited talk today. So multiple cleans means we need many cleans, many different pairs of cleans. So I hope you should keep it in your mind. And so this is a joint work with Abel Callum, Santana Sarkar, and Willy Meyer. And okay, let's skip this. So let us directly see what HERA is. HERA is a stream cipher designed to be efficient in CKKS FHE scheme and especially to the transciphering framework. Yeah, and HERA was designed at Asia Crypt 2021. And yeah, before this work, there is no third-party cryptanalysis. And this figure gives a complete description of how the encryption algorithm works. So this is the key string words. It composed of 16 words over a finite field FP, Z1, Z2 until AZ16. And here we denote the round function of HERA by F. So you can see it's a very common SPN structure. So this is the linear layer. So indeed, it's just a invertible matrix. And then S-box layer, the same at S-boxes, and then the key addition. And you may observe that this is something different. So you can see that the round keys are indeed obtained by the element-wise multiplication between a vector composed of C and the key stream key variables. More specifically, you can check this figure. So the input A1, A2 until A16 is a constant vector, and the matrix asset is fixed, and it's invertible. So this is indeed different from the raster design, because as you may know, in raster, it's also an FT friendly cipher. The linear layer will change every time to generate the key string words. Here in Hila, it's also use something similar. So I mean, the cipher is so where is the randomness? I mean, here the randomness is it's caused by the round keys. So as I already said, this is something special. So here, each time to generate a new key string Z1, Z2, Z16, we will need to refresh these constants Cij. In other words, before generating key string, we need to generate some random constant Cij. And then after getting the values of Cij, we get a concrete instance of Hila, and then we run this English algorithm and get the key string word. So it's very different from common designs, and you know, like differential analysis cannot work anymore because it's just like a moving target. It changes every time to generate the output. So let us focus on how these randomly generated constants are generated. Yeah, so these Cij, they are indeed the output of an XOF. So, and the input of the XOF is an IV, and IV is composed of a nonce and a counter. And the length of IV is related to the provided security levels. So it's in Hila, it provides 4 different security levels, 8-bit, 100, yeah, like this. And as already said, after getting this constant Cij, we can run the encryption algorithm and get the key string word. And indeed, this, I mean, for such a design, because it's moving every time, it's a moving target. So the most effective attack becomes the algebraic attack, and especially the linear relation attack, because you can easily observe that each key string word can be expressed as a polynomial in the key variables, in these 16 key variables, and we also know the S box is just the power map x to the 3. So for R rounds of Hila, the degree of this polynomial is simply 3 to the R. And so if we can use sufficiently many IV to generate sufficiently many key string words, and we can expect to we can have so many equations. And note that for a polynomial in 16 variables of degree 3 to the R, there are at most so many monomials. So after we get so many equations, if we name each different monomial with a new variable, then we have the number of equations is the same with the number of variables, and we can use Gauss elimination to get the solution of the key variable. And the complexity of this attack is simply to perform the Gauss elimination on the coefficient matrix, and omega is the algebraic constant for Gauss elimination. And as this is the most effective attack, so the designers selected the secure parameters for Hila in this way. So they choose the minimal R such that TR2 is larger than 2 to the lambda, because it has to provide lambda bit security. So as you can see, there are 4 different parameters. And yeah, to understand the concrete codes to break R rounds of Hila with different R and omega, we also I mean, we calculate the cost to break R rounds of Hila with different R omega with the linear relation attack. So as you can see, yeah, indeed, if we only use R minus 1 rounds, yeah, we can break it on the omega equals to 2. And if we use some more conservative choice for omega, like 2.8 or 3, we can see that we can break R minus 2 rounds, but we cannot break R minus 1 round. So in the conservative setting, we have 2 rounds for the security margin, but if we use omega equals to 2, we only have 1 round. So what does this mean? This means if we can have equations of degree 3R minus 1 for R round Hila, we can break Hila under the same assumption made by the designers, that's omega equals to 2, because this is how they choose the secure number of rounds. And if we, I mean, a more realistic setting that we choose the algebraic constant omega as 2.8 or 3, then we can reduce the security margin from 2 rounds to only 1 round. So this, yeah. So the problem now becomes how to set up low degree equation. That's we want to set up an equation of degree 3 to the r minus 1 for r rounds of HeLa. This is indeed equivalent to peel off the last nonlinear layer. So how can we peel off the last nonlinear layer? And our idea is kind of similar to the differential attack. So we will use a keystream pair rather than a single keystream. And this also makes our attack different from algebraic attacks on other FHE friendly ciphers. And the overall procedure is composed of 3 phases: the offline phase, the online phase, and the phase to solve equations. So at the offline phase, we will collect many sufficiently good IV pairs. As the online phase, we will, for each good IV pair, we get the corresponding keystream pair. And if the keystream pair satisfies certain conditions, yeah, we can set up a low degree equation. And then if after collecting many such equations, we solve it with the linearization technique. That's to simply run the Gaussian elimination. So the key problem now is obvious. That's how to define a good IV pair, because this is the starting point of the framework. Note that IV is the input of the XOF, and the output of the XOF is the random generated constants. So we tend to consider the output of the XOF, more specifically, instead of consider conditions for IV, we consider conditions on CR prime. So they are used for the last round key generation. So CR, they are all vectors. And if we can have conditions on these 2 vectors, then we obviously have conditions on the IV pairs because it's the input of the XOF function. So note that our idea is to peel off the last nonlinear layer. That's we need to peel off the last Xbox layer. And here we denote the input of the Xbox layer by YR-1. Note that it is a vector of 16 words. And we also denote the output of the last Xbox layer by WR. So it's also a vector of 16 words. So how do we peel off the last nonlinear layer? So that's indeed very similar to a differential attack. The idea is quite simple. So let us consider the S-box in the last round. So there are 16 S-box. Let us consider a random S-box. And if we can observe the output of this S-box is identical, then we must know that the input pair is identical. And according to by exploiting the property that the S-box is a power map, that's exterior 3. And if we can observe this equation, this condition beside in the output pair, and beta is a non-constant, is a non-value, then we can also observe this this relation inside the input pair. Note that this is the input of the last Xbox layer. So if we express it as polynomials in K, it has degree 3 to the R-1. So the problem becomes how to observe these things. And yeah, at the first glance, you can see that the output pair, we consider the inverse function. The output of the Xbox is obviously related to the key because we need to compute it with the key string and the round key. Yeah, it's just the inverse the last linear layer. And but note that our goal is to observe this relation, but this is related to the key. But if we do not guess the key, we don't know this value. Then how is it possible to check this relation and get the concrete value of beta? Our idea is quite simple. We just kind of differential, like similar idea. So note that CR and CR prime are public to the attackers, and we also assume, and it's also common to assume the key stream words are public to attackers. And we know both equation 3, equation 4 can be checked without the knowledge of K. And indeed, if you check this expression, and if equation 3, equation 4 holds, we must have this relation. And the beta can be easily calculated because all of them are public. So we have solved the problem how to check the relation for the output for an output pair of an S-box and how to get the value of beta. And so it's to be very clear what the offline phase and online phase will be. So the offline phase, note that we want such equation holds, and they are output of an XOF. So it's, I mean, so if we can collect such output pairs of the XOF, then the corresponding IO pair is good. And then as the online, and they do not require the knowledge of K, but at the online phase, we need to check the conditions on the key stream. So we need to, so this is why it's called online phase, because we need, to use key to call the encryption oracle. And we can get the key stream and check this relation. If they hold, then we get a low degree equation according to a certain S-box in the last round, according to the input pair of a certain S-box. But as you may know, you may observe, so there are so many conditions here. Note that they're of the same scalar, almost get so too many conditions. So we want to reduce the number of such conditions. The idea is just to involve the guess and determine strategy into this attack. So more specifically, note that our goal is to check this relation. And we have this expression, so we can guess N1 key variables, and then we will know the value of this N1 variables. Then we only need to check equation 5 and equation 6, because data can be easily calculated according to the guessed key variables. And this is obvious. If this hold obvious according to this expression, we can obviously know this hold. But of course, since we use guess and determine, there is an overhead. So we need to repeat the attack p to the n-1 times. So now it's to be very clear what we need to do as the offline phase. So our goal is to find an IV pair such that we can get the output satisfy equation 7. Yeah, and indeed this equation is indeed to convert it to finding the cleans, such cleans on the output bits. And we suppose the length of outputs is, the length of this verse is L. Then, and we suppose we need so many cleans. Then the complexity to find so many cleans is just this. It's just a burst attack. And then after getting so many, cleans, IV pairs, then we get the corresponding key stream pair, ZZ prime. And then for each key stream pair, we get the corresponding N1 key variables and compute data and data prime. And then we check whether there exists such an S-box such that we can construct low degree equations from the input pair, from the relations inside the input pair. And this holds with probability of this, about this. So, and if there exists, we get a low degree equation of degree 3 r-1, and we expect to collect so many equations. So then we solve this equation system with Gauss elimination, and the complexity of the online phase and the solving equation is quite easy to get. Just it's quite easy. But remember that there are some additional constraints. The first constraint states that we need 2 to the b cleans of the output of an XOF, and the input of the XOF is 3 lambda by 2. So to get so many cleans, we have this first constraint. And for the second constraint, it states that we can collect so many low degree equations. from 2 to the B input pairs. And the last equation states that the same key can only be used to encrypt up to 2 to the lambda by 2. I mean the counter. This is the maximum value, and the maximum value of the counter is 2 to the lambda by 2. So we can see that according to our analysis, as you can see, maybe it's not so, maybe I should give a figure, but you can see, according to our analysis, HELA is not affected by our attacks if for the, if it only provides 80-bit security or 128-bit security, but for the remaining parameters, we can break it, under a very optimistic assumption on the algebraic constant. And if you're using more conservative choices, we can reduce the security margins from 2 rounds to only 1 round. And at the last, I want to know whether it's possible to apply our method to HELA to the cryptanalysis of a battle. But it also uses the randomized key schedule, but it's quite different. But if you are interested, you can check it. That's all. Thank you.
Is there any question for Fukang? So I only have one. One of the issue is that the last S box is a power mapping. If we change the power mapping with the S box with I don't know, a binomial mapping, is there similar attacks that will come with collisions or not really?
It's in this case beta is set as 1, so we cannot just the output's the same.
Okay. Okay, so that's harder to get. You need concrete collisions.
Indeed, it will increase the complexity of the offline phase by about P. The size. Okay,
is there any more questions? No, so I think we can thanks Fukang and all the speakers of the session and the session. Thanks.